It's a winter Saturday and you're pulling your friend along a level snow-covered road on a wooden sled. Doesn't that sound nice? The rope pulls up on the sled at 25 degree angle above the horizontal. So let's start drawing this since we're at it. There's the 25-degree angle above the horizontal. Call that theta. The mass of the sled with your friend on it is 45 kilograms, so m equals 45 kg. With what force must you pull in the rope in order to walk forward at a steady speed of v equals 1.3 meters per second? Please express your final answer in the box provided in newtons to two significant figures. So there's tension in the rope. So first thing we want to do is draw a free body diagram of the sled. So listing all the forces, we've got the tension, which is pulling up at some angle theta. We'll draw that on there. The gravity force pulling it downwards. It's a level road, so we've got the normal force pushing it upwards. And I guess we've also probably got kinetic friction force pulling it backwards, F sub k. And we have a couple of things here. We know that F sub k is equal to mu sub k times n. And also we should set up some axes here. Let's call x towards the right and y upwards, so that if we have the tension and we break it down, this will be t sub y, this will be t sub x. Here's your theta, so that the sine theta is t sub y over t, so t sub y is equal to t times sine theta, and t sub x is equal to t times cosine theta. Okay, so that's an analysis of the forces. This v is constant, and so what that means is that the acceleration is 0. Okay, or the velocity, I guess, is constant. So acceleration equals 0. So this is equilibrium. So all we need to do here is just balance all these forces in the x and y directions. So let's make a table. X and y. I'm going to list all the 4 forces that are acting on this. Let's start with tension, and we'll go clockwise. We've also got mg, and we've also got F sub k. So I'm going to call that F sub k equals mu sub k times n. And we've also got n, right? So let's just find the x and y components of all these. T is, we've already worked that out. So in the x direction, that was t times cosine theta. In the y direction, that was t times sine theta. mg is just acting straight down, so it has 0 x component and has negative mg as the y component. As for kinetic friction, it's acting in the negative x direction, so it's negative mu sub k times n, and there's 0 y component. And the normal force is just acting up, so it's got 0 x component, and it's acting up like that. So now, to find the net force, we just add all these things up. So it's going to be t cosine theta minus mu sub k times n equals 0, because it's an equilibrium. And the y components is t times sine theta minus mg plus n is equal to 0. Okay, so counting up the unknowns, I'm looking at this mu sub k, and we don't actually seem to know it, but we know that it's the sled is wood and it's snowy ground. So I went to the first page of the test and I see wood on snow. We actually have static and kinetic frictions listed here, and it says the kinetic friction mu sub k is 0.06. So we actually do know this. So mu sub k equals 0.06. That's from the front page of the test. So we know, we don't know t, we know theta. Theta equals 25 degrees. We know mu sub k, and we know g. We know the mass is 45 kilograms. The only things we don't know are n and t. So it's 2 equations, 2 unknowns. We're going to solve for n in one of these equations and then plug it into the other equation to eliminate it and solve for t. So why don't we use the y equation to solve for n. So we'll have here that we'll just have to pull these things over to the side. So let's use this y equation to say that n is equal to mg minus t times sine theta. Okay, so now we're going to plug that in to this equation from the x component. So something like that. And what that's going to look like is that t times cosine of theta minus mu sub k times all that stuff, mg minus t sine theta equals 0. So, and we just have to solve that for t. So multiplying through here, we have t times cosine theta minus mu sub k times m times g plus mu sub k times t times sine theta equals 0. So collecting like terms of t and pulling this over, we've got mu sub k times mg is equal to t times cosine of theta minus, or say plus, mu sub k times sine theta. So that the tension here is equal to mg times mu sub k over mu sub k sine theta plus cos theta. Plugging in the numbers for all of that, I've got 45 times, that's 45 kilograms times 9.8 meters per second squared times open bracket 0.06 divided by 0.06 times sine of theta, which is 25 degrees, plus cosine of 25 degrees, ending all my brackets there, and I get 28.40. So to two significant figures, that's 28 newtons. That's the tension, but that's also equal to the force that you're pulling the sled. And does that make sense? Well, it's not accelerating at all. All you're doing is keeping it in equilibrium. And you've got this 450 Newton force pulling it down, and a very small coefficient of kinetic friction, 0.06. So something a lot less than the weight is what's needed to pull it along, which is what makes it such a pleasant Saturday.